In the present video, we're going to talk about functions in the .numerics plugin, which has applications for linear algebra and the solution of ordinary differential equations. For that purpose, we're going to start with this particular worksheet. The plugin should be available in your online gallery. I already have it in my local storage. It's simply called .numerics. And when you include those functions in here, you can look them up, and it has these functions. The first four are related to solving ordinary differential equations. The next ones are on linear algebra, and we're going to see the applications of them. For linear algebra, if you have a matrix, I'm going to create a 3x3 matrix here. These functions are excellent for calculating eigenvalues and eigenvector functions that are not available in Math Studio. And so the name of the function is very long, dn len all eigenvalues a, but you can easily insert it from the collection of functions right here. Select .numerics, select dn len algebra eigenvalues or eigenvectors. And so the eigenvalue will give you the values of the eigenvalues of a matrix. If you recall, the eigenvalues result from the following matrix equation. This equation, where the values of lambda are called the eigenvalues, and the values of x are called the eigenvectors. This equation can be rewritten if we move the right-hand side to the left-hand side in this way. And this function is such that it's non-trivial if this determinant is equal to 0. When we take the determinant of A minus the identity matrix times lambda equal, the determinant equal to 0 produces what is called the characteristic equation. And the solution to the characteristic equation are the eigenvalues. But this function will give you the eigenvalues right away. The function eigenvector will give you a matrix, and the columns of the matrix correspond to the eigenvectors for each one of the eigenvalues shown above. And so I have extracted those columns in here, and they turn out to be unit eigenvectors. The norm E, which is the Euclidean norm of each vector is equal to 1. Other programs, this is actually not relevant to the case. I was just checking something in here. I'm going to delete those so it won't get confusing. But basically, the magnitude of this vector is equal to 1. These are unit eigenvectors. And they have the property, if the matrix is symmetric, like in this case, then the eigenvalues are real numbers. This is the case, for example, for finding the stresses, the principal stresses in a stress situation in solids or fluids. And so in that case, the eigenvectors are orthogonal to each other. So for example, if I do U1 times U2 and I do it, sorry, not that one. I need to select the entire product. No, I'm not doing the right thing here. Let me try this. U1 dot U2 transposed. Oh, U2 has not been defined at that point, so I need to drag this down a little bit. Wrong way, sorry. It has to be U dot 1 transposed multiplied by U2. That's the dot product. And that should be giving me 0. That's 10 to the minus 16. So that's what I wanted to prove. That for a symmetric matrix, the eigenvectors are orthogonal to each other. Another function that's available in the .numerics is the matrix inverse. But that actually is not necessary, because in Math Studio was just typing a to the minus 1, you get exactly the same result. For linear algebra, we also have the least square fitting problem and the solving a linear system. We can start with this one first. If you have, for example, a system of n equations and n unknowns, in this case 3 by 3. You can extract the coefficients of the left-hand side into a matrix that we're going to call A. That's called the matrix of coefficients. Then the values on the right-hand side form a vector, which is called the right-hand side vector. And the unknowns will be put together in a vector corresponding to x1, x2, x3. And so this system of linear equations is now represented by this matrix equation, A times x equals B, that can be written in this way. And you can see that doing matrix multiplication, that this matrix product will give me these three linear equations. The solution can be found simply by doing this, because if we start with this equation and then we multiply both sides on the left hand side with a to the minus 1, and then we realize that the product of a to the minus 1 times a is the identity matrix. And that the identity matrix multiplied by a vector is just the same vector. Then the solution to this equation is this result that I calculated in here. And so you can calculate this in the numeric equation or function len alt solve, or using this expression. Now the problem of least square fitting can be illustrated by this linear fitting, where I have only two parameters, beta 1 and beta 2, but I actually have four data points. The second column here represents the value of x, and this represents the value of y. And so that I could build a matrix called uppercase X, where the first column is number ones and the second column is the values of X. Beta is the coefficients, beta 1 and beta 2, and Y is the values of Y. So that these three are related by X times beta equal Y. And so if I replace the values of X, beta, and Y into this equation, I get this result that will result into a system of four equations. Since I only have two unknowns, the system is overdetermined. I have more equations than unknowns. And so the only way to obtain a result here is by using least square. That means finding the values of beta 1 and beta 2 that minimize these results in a least square sense. And so for a particular example, I'm going to replace my generic equation here by these values and these values of y. And then it turns out that .numeric offers three functions. And I'm going to show you here what all those three functions. So I've got the .numerics, and these are the LLS COF that uses what is called orthogonal factorization. Then this one that uses either the QR or LQ factorizations, and then the one that uses the singular value decomposition. Now the details of those methods, you're going to have to look them up. This is called the orthogonal factorization. This is called the QR or LQ, and this is going to call the singular value decomposition. I'm just showing you how you can use those particular functions to solve problems. And this is the matters related to linear algebra. There's one more function of interest, and that is calculating the inverse matrix. And you can use this function, the n matrix inverse A, or simply a to the minus 1. And with that, I'm going to stop this video and talk to you about solving ordinary differential equations in the second part.